Welcome to Chapter 8, titled Conservation of Mechanical Energy. This chapter is a continuation of the previous chapter. In this chapter, we'll explore the interplay between kinetic and potential energies. That is, a reduction in one type of energy results in an increase of the other. That is because mechanical energy is conserved. The fact that conservative forces stored potential energy in our system as they did work on it guarantees us that this will be true. But the big question is, what happens to the energy of the system if one or more non-conservative forces do work on it? The answer is, well, quite simply, the system will lose this energy, but the external environment around the system will gain it. That is because energy can neither be created nor destroyed, only transformed from one form to another. We begin by considering the case where only conservative forces act on the system, and so we can say that the total mechanical energy of the system is conserved as long as the system remains isolated. That is, the mechanical energy of the system will be made up of any kinetic energy the system contains added to any potential energy the system contains. And conservation of mechanical energy basically says that any change in kinetic energy will be balanced by a change in potential energy so that no change in energy can occur. No net change in energy can occur. In other words, energy will be conserved. Okay, so now let's go back and look at the changes in kinetic, changes in potential. The change in kinetic energy is K final minus K initial. The change in potential energy, U final minus U initial. If we rearrange the terms where all the final energy is written on the left-hand side of this equation, the initial energies are transferred to the right-hand side of the equation, what this again says is that at the end of an energy process, the sum of the final kinetic and the final potential should equal the sum of the initial values. Now let's consider, based on the definitions of kinetic and potential, how we might translate these terms. K final, 1/2 mv final squared. U final can either be gravitational or spring. In the case of gravitational, mgy final. In the case of spring, 1/2 kx final squared. And that should equal the initial kinetic energy, 1/2 mv initial squared, and again the initial potential energies, mgy initial plus 1/2 kx initial squared. If any one of these energy terms is 0, for example, if the system does not contain a spring, so that there is no processes that occur to produce potential energy terms for the spring force, then certainly we would only consider 1/2 mv final squared plus mgy final equaling the sum of the initials. Let's view a video animation regarding conservation of mechanical energy. This is a familiar video that we watched in Chapter 7, but is relevant in this chapter as well.
The glider starts off with 0 kinetic energy. Because the weight can fall a distance h before it hits the floor, it has a potential energy equal to mgh. Mgh is the work required to lift a mass to a height h. When the glider is released, the force applied to the glider by the weight accelerates the glider. thereby causing it to gain kinetic energy. At the same time, the weight is also accelerating, so its kinetic energy increases as well. The weight's potential energy has applied a force to a mass over a distance. When the weight reaches the floor, it and the glider have kinetic energy, but no potential energy. In this example, energy is converted from its potential to its kinetic form.
So again, conservative force is doing work on the system, conserving the mechanical energy. How about the big question that we posed earlier, and that is, what if there are non-conservative forces also acting on our system? In this case, we can no longer say that a change in kinetic will be balanced by a change in potential, because now the changes in these two forms of energy is no longer zero, but is equal to the work which is done by the non-conservative force. For example, if friction was the non-conservative force, the system can never recover the energy that it lost to the force of friction as it did work on it, but we can still balance things out by saying, well, any loss in the combination of the kinetic and potential that the system started out with can be accounted for as the transfer of energy out of the system by the work that was done through the non-conservative force. Okay, let's continue on with the example of friction. Delta K plus delta U. This time we'll say specifically it's kinetic friction that is doing work, and the fact that the work is negative means that the term on the right hand side should be a negative number. In this case, rearrange the terms. Final kinetic plus final potential equals initial kinetic plus initial potential minus that which was lost to friction, so that we can see that the final energy will be some number less than the initial energy, and that will be accounted for by this term here. So the amount of work that is done by friction is actually converted to non-recoverable energy. The universe gains this energy, but the system loses this energy. Let's view an animation in the case where kinetic friction is present and therefore doing negative work on the system. We have a block with an initial velocity that we will click on the start button. It will be 3 meters per second. There's the coefficient of friction between the block and the surface along which it will ride, and we will view how the values of kinetic, internal, and total energy compare. Click start, and we see that the block started with an initial kinetic energy, otherwise it wouldn't have initiated motion. However, because friction was doing work on it, eventually the block lost all its kinetic energy. However, the energy was not destroyed, it was merely converted to internal energy. Heat either to within the internal structure of the block, to the environment, to the air around it, but nonetheless the block itself as a unit does not contain this energy anymore. The universe still has the energy, that is, the total energy is still 13.5 joules, but not the system. The next term that we want to study is the term power, represented by the letter P, the unit of which is the joule per second, which is also known as the watt. And power can be thought of as the rate at which energy is transferred. In other words, the rate at which work is done. Now, average power only takes into account, on average, the work which is done for some interval of time. So work over delta T, which can also be written as F dot delta R over delta T, and we can rewrite delta R over delta T as the average velocity of the system. So that power can be determined by taking force dotted with the average velocity. If we're interested in knowing the power at every instant in time, then we have to consider the rate at which work is done at every instant in time. And so in this case now, F dot dr over dt, where we can see dr over dt is the instantaneous velocity that the system has as the force acts on it. Some interesting information about the unit of energy and power. Of course, in the SI system, work, kinetic energy, potential energy are all expressed in terms of the joule. In fact, we can think of the joule as the energy necessary to lift a 1 Newton, say, red apple, a distance of 1 meter. In power, the SI unit is the watt, where 1 watt is 1 joule per second. The kilowatt hour, which is actually a unit of energy, because it is power times time, and power times time is equal to energy. So the kilowatt hour is how FPL bills us, and it takes into account the consumption of energy, in other words, the power which is consumed multiplied by the amount of time over which the appliance is being used. So 1 kilowatt hour is equal to 3.6 million joules. The foot-pound is the unit of work in the British engineering system, and power is measured in terms of horsepower, where 1 horsepower is 550 feet times pound per second. There is a conversion which relates 1 horsepower to 746 watts. The last topic that we want to look at is a very interesting application of conservation of energy, and that is the escape speed. For example, if we were to send a probe from the Earth and we did not want this probe to ever return back to the Earth, we wanted to send the probe an infinite distance away, in the same way that we sent the Pioneer 10 spacecraft after a visit to the solar system on its journey out of the solar system, which it was just crossing the orbit of Pluto back in 1987. So it is still journeying out away from the solar system into outer space. To be able to send such a spacecraft to escape the Earth's gravitational pull, the spacecraft needs to be given an initial velocity that allows it to do that. So now let's consider our space probe, our satellite, our spacecraft, to have a mass m, and to be projected upward from the Earth with an initial speed so that it will reach some maximum altitude where it is said to be at infinity. For example, never to return to the Earth. Well, we assign the initial kinetic energy of the satellite as 1/2 mv initial squared. The initial gravitational potential energy of the satellite and the Earth system is what we saw in the previous chapter, chapter 7, except that the initial position is the radius of the Earth, so that initially the potential energy is minus g, mass of the Earth, mass of the satellite, divided by the radius of the Earth. Now, because our spacecraft is going to reach some maximum location in space, and if we treat it as a maximum altitude, we know that it will stop eventually, then we ask ourselves, at this location, say infinitely far away, what would its potential energy be? Well, that would be our zero reference. So this is our reference, our zero reference of potential energy. So when we consider here then initial kinetic energy, the sum of these two terms should equal zero, since the final sum of kinetic plus potential should also equal zero. And so these two terms have to add up to zero, or should equal zero when added in this form, and we solve for the velocity that allows us to do that, and we get, for the Earth, with the mass of the Earth and the radius of the Earth, an escape velocity which is 11,200 meters per second. That is equivalent to about 25,000 miles per hour. To escape the solar system, Pioneer needed to have something like at least 30,000 miles per hour, which in fact it did have, and thus was able to escape the solar system, cross the orbit of Pluto several years ago, and continue on with its journey. Let's watch a video regarding the escape velocity of the Earth.
4, 3, 2, 1, and liftoff.
A rocket lifts off from Earth. It carries a probe destined for interplanetary space. To accomplish its task, the probe must escape the negative potential energy of the Earth's gravitational force. Since the gravitational potential energy is defined to be zero at infinity, a probe can just escape the Earth's gravity if its total energy, gravitational potential plus kinetic, is zero. By writing this condition down mathematically and rearranging terms, we see that there is a minimum speed, called the escape speed, that a probe must have to escape the Earth's influence. The escape speed does not depend on the mass of the probe. Conversely, if an object started at infinity with zero kinetic energy and, influenced only by the Earth's gravity, fell all the way to Earth, the speed it would have on impact would be